Hello, everyone, and welcome to another episode of our weekly Cloud on Air Innovator Series. I'm Chloe Condon, a cloud advocate at Google, and I'll be your hostess with the mostest each week as we dive into different technical topics, watch demos, and learn best practices from some of our top experts here at Google. If you joined us last week, or the week before, or the week before that, welcome back. And if you're new here, welcome. We're so excited to have you join us and be a part of our community. Now, if you're joining us live, you may notice that we have a live chat. Feel free to use this space to interact with other viewers and ask any questions that you may have about the topics being discussed in today's session. One of our moderators will try to answer you live in chat, or you may just be lucky enough to have your question answered live on the air during our question and answer session with our speaker at the end of this presentation. And if you're not joining us live, join us next time. Make sure to register for one of our upcoming sessions so you can join in on the fun live as it happens. To learn more, check out cloudonair.withgoogle.com, and you'll be able to take a look at our previous streams and register for all our upcoming sessions. You can take a look at previous sessions, or take a peek at some of our upcoming ones where we'll be covering cloud topics like data analytics, GenAI, security, developer productivity, and so much more. We have a great library of content for you to look through, so feel free to check out our catalog of videos from Google experts that you can watch on demand for free. Without further ado, let's begin today's session. Take it away.
The pace of innovation in generative AI has truly been unprecedented this past year. No doubt this is a phrase you've heard over and over again. And yes, we are in an exciting time when it comes to GenAI innovation, with new announcements, new capabilities, new research seemingly coming out every single week. But delivering value with AI is more than just adding the letters A and I to your product and service name. Something you've no doubt heard a little bit about this year as well. Delivering value really requires production readiness and scale for your AI models, with the flexibility to deeply integrate into your software stack. Hello and welcome everyone to this session, Unlocking AI Innovation, Deploying Generative AI Models in GKE. During this session, we'll pull back the curtain and talk a little bit more about the platforms and infrastructure that make production scale generative AI possible, as well as share some exciting announcements that will help you, the AI practitioner, up-level your GenAI-powered apps, products, and services. So let's jump right in. My name is Brandon Royal. I'm a product manager for Google Kubernetes Engine focused on AI, and I'm joined by my good friend, Mofi. Mofi, you want to quickly introduce yourself?
Yeah, thanks, Brandon. My name is Mofi. I'm a developer advocate at Google focusing on GKE and running AI workloads on GKE. Excited to be here, excited to learn more, and share some exciting stuff with you.
Awesome. Yeah, thanks, Mofi. It's going to be a lot of fun. So we've got a jam-packed session. As always, lots of stuff to go over. And we really hope to sort of bring you along here as we explore platforms and infrastructure for generative AI on GKE. Let's first start, or we will first start with the sort of state of generative AI models, kind of where we are and sort of where we're going. We'll talk a little bit about open models on Google Cloud, sharing some exciting announcements from today. And then we'll go much deeper into AI training on GKE, inference on GKE, as well as some of the very powerful AI accelerators, TPUs and GPUs that can be orchestrated with GKE for your generative AI platforms and workloads. And then the best part, of course, is I'm going to be handing it over to Mofi here towards the end, and he's going to bring us home with a demo, pulling this all together. So really excited for that. So, of course, generative AI models are evolving quite rapidly. I think this is not new information to anyone on the call here. But ultimately, we do need to recognize that these capabilities are continually improving. New capabilities, better reasoning, better performance. And we're seeing this across both models like state-of-the-art models like Gemini, as well as in open models. So in open models, we're really sort of seeing a rapid set of innovation in the AI community. And there's a whole bunch of reasons for that. Flexible deployment, so the ability to sort of deploy these models anywhere you want. The ability to focus those models or optimize and tune those models for very specific tasks using fine-tuning strategies, or the ability to sort of optimize the resources behind each one of those models, ensuring that you're utilizing your precious resources as effectively as possible, delivering the best price performance. Now, of course, generative AI in 2024 isn't without its challenges. So last year we were talking a lot about sort of prototyping and ideation. Now, this ability to deliver AI powered features quickly remains to be a challenge. And of course, we all know that an AI model in itself isn't valuable. It's really when that AI model gets to our customers and really is deeply integrated with an application or a feature where it actually starts to deliver value. So there's still quite a lot of work to do in making sure that that model gets deployed out so it's production ready, scalable, secure, and then integrated into your stack. So that's a challenge we'll talk about. Of course, AI hardware obtainability and utilization is still a challenge. We know that these GPU resources, these accelerator resources and TPUs, these are still difficult to come by for a lot of organizations. So, this is a challenge that we also want to help to address as well. And then, of course, price performance is key. This ability to deliver models in a price performant way, both for inference as well as for training, is a key challenge for a lot of organizations. So, we really want to help to ensure that we're delivering the best solutions to improve that price performance for all models over time. And so, Kubernetes has long been and continues to be a really solid foundation for AI, and particularly for open models and open LLMs. And there's a whole bunch of reasons for that. In terms of flexibility, Kubernetes provides an ability to deploy any kind of framework that you want and that you want to use with a rich ecosystem of tools, both within the ML ecosystem as well as within the container and Kubernetes ecosystem, allowing users to ultimately have portable artifacts that they can deploy, portable models and scripts and tools that they can use across their various platforms. Kubernetes has lots of experience delivering performant applications, and that's, of course, no different from AI, where we can now orchestrate AI models across massive scale, utilizing some specialized AI infrastructure resources as well. So that ultimately helps us to deliver that really key performance that our customers are ultimately looking for. And then efficiency, not only in terms of operational efficiency, if we're managing these very large clusters, lots of models distributed across multiple regions, we need to operate those efficiently as possible, having clear observability so we can see exactly what's going on. But we also want to ensure that the resources that we're allocating for training or for inference are also utilized quite effectively. So we want to bin pack and do other things that Kubernetes is just naturally very good at to ensure we're delivering the most performant and efficient applications. And Google Kubernetes Engine, this is really our sort of answer to having the most cloud native infrastructure for both your training and your inference workloads for customers that are really looking for that flexibility, that portability, and that efficiency that Kubernetes naturally delivers. With Google Kubernetes Engine, we can help deliver industry-leading scale with up to 50,000 TPU chips in some recent research. So massive scale in terms of the underlying AI infrastructure orchestration that we can do, also to very large cluster sizes of up to 15,000 nodes per cluster. So very large scale, which is of course critically important in all things AI. We also help to deliver superior price performance with both GPUs and TPUs. And we do that in a whole bunch of different ways, everything from multi-tenant job queuing to our ability to do GPU sharing, fast pod startups. These are all things that ultimately are just helping customers to continually improve the price performance of their AI workloads. And then efficient operations. I mentioned that earlier. GKE takes that up a level by offering capabilities like GKE Autopilot, a mode of operation that essentially abstracts a lot of the underlying nodes away so users can focus on their AI workloads and their apps. And that helps drastically in helping teams be operationally efficient and helping their applications to scale as needed. And then, of course, this is all a fully managed Kubernetes experience for both your AI workloads as well as apps and stateless and stateful, and as well as data. Anything can essentially, or a lot of different workloads can run on GKE, and we're really going to help to, as one of the top contributors to Kubernetes, really help to make sure all those pieces work together. And so really the proof is something we're quite proud of, with organizations like 70% of the most innovative organizations that are building generative AI applications and models are choosing Google Cloud. These are the companies that have the most sophisticated and knowledgeable teams in the space, and they're really choosing Google Cloud because of that choice and that flexibility. It's not just GKE, it's the underlying infrastructure, it's the choice of services within the portfolio that really helps to set Google Cloud apart. And they really choose Google because AI is essentially in our DNA. Now, what do we mean by that? AI is in our DNA. We certainly talk about AI a lot. Well, there's quite a lot to unpack here, right? First and foremost, research, AI research in particular, has been a critical part of Google's culture, with 3,000 expert researchers that have produced over 7,000 research papers. And these are, all of the innovations that sort of have made AI as we define it today possible, is really thanks in part to a lot of these research efforts. Things from the transformer architecture to the mix of experts. There's a whole bunch of other examples where that research really is critical. So we bring that to bear. Of course, leadership in all the foundation models, including Gemini and a whole bunch of other models that predated Gemini. We're continuing to innovate with our first-party cutting-edge foundation models, but we also care deeply about the ecosystem. We provide sort of contributions to things like TensorFlow and PyTorch, as well as things like JAX and XLA, all tools that are really designed to help organizations to innovate in the open ecosystem and take advantage of sort of the work around the community. So that's obviously critically important. And we talked about Kubernetes, of course. Kubernetes is, from an infrastructure perspective, something that Google has invested deeply in, which is critically important to orchestrating AI workloads at scale, as I mentioned earlier. And then, last but not least, Google has world-class infrastructure that's really purpose-built for generative AI applications, with massive storage, networking, container orchestration, and scale that allows us to deploy in the cloud, as well as have the ability to deploy to sovereign clouds as well, giving organizations a level of control over their data that's necessary. Now, last December, Google announced Gemini, a family of state-of-the-art multimodal models. And Gemini is really built from the ground up with multimodality in mind. That means reasoning seamlessly across text, images, audio, video, and code. And the latest release of Gemini, Gemini 1.5, delivers dramatically enhanced performance with the most efficient architecture. Now, the first model we released, really for early testing, introduces breakthrough experimental feature for long context understanding. So that means that context length can be as much as 1 million tokens, which is quite significant. Now, we've built the Gemini models responsibly from the start, incorporating safeguards and really working together with partners to make it safer and more inclusive for everyone. And we're really proud because that innovation continues. As of today, we're announcing Gemma. Gemma is a new family of lightweight, state-of-the-art open models built with the same research and technology used to create Gemini models. Accompanying our open weights, we're also releasing tools to deliver developer innovation, foster collaboration, and guide responsible use of Gemma models. As developers, you can now deploy Gemma directly on GKE to create your own generative AI apps from prototype all the way to production. And with Gemma on GKE, you can do everything from deploying custom fine-tuned models in portable containers alongside your applications. You can customize the model serving and infrastructure configurations without the need to provision the underlying nodes or maintain those nodes. You can integrate AI infrastructure fast with the ability to scale to meet the most demanding training and inference scenarios. So we're really, really excited about this opportunity for the community and the ecosystem to collaborate around Gemma, the new open model. Now, Gemma models share technical and infrastructure components with Gemini. That's our largest and most capable AI model that's widely available today. Now, these enable the Gemma 2B and 7B to achieve the best-in-class performance for their sizes compared to other open models. For more information on these benchmarks and other technical details on the Gemma model, you can refer to the technical report at ai.google.dev/Gemma. We're excited for you to start building new innovative GenAI apps on Gemma on GKE. Now, speaking of building apps, let's talk a little bit about training and how GKE as a training platform can meet the most demanding model training jobs. Everything from job scheduling, doing scaled training and fine tuning, all the way down to optimizing those resources. Now, a lot of that starts with job queuing. So when we talk about large multi-tenant clusters and jobs for training workloads, we ultimately need to talk about a job queuing system that's going to help to manage that scale. Now, queue is a new feature within GKE, actually part of an open source project that allows for scaled queuing of all kinds of different native Kubernetes jobs objects. It can help with things like execution order, so ensure that jobs are being executed in the proper order, which is, of course, important in fine-tuning and training scenarios. It can allow for budgeting, so you can actually have control over budgets for different teams. And then ultimately, you can, as an administrator, set policy for how these jobs are actually executed and by what team, ensuring that resources are available for that team and for that job before it's ultimately deployed. And this is really critically important to sort of enhance the job scheduling capabilities within Kubernetes and within GKE to support the very large scale training needs of generative AI models. Now, another challenge that I mentioned earlier was this idea of resource obtainability. So how can, as an organization, I get the resources I need, the GPUs or the TPUs or the specialized compute that's often necessary to train and fine tune very large models? So Google has what's called dynamic workload scheduling, or DWS. And this is a new capability for obtainability of these these specialized accelerators like GPUs. Now, this works across multiple platforms, multiple surfaces within GKE or within GCP, including GKE, and offers the ability to essentially request the resources that are needed for a given job. And when those resources are available, they will be allocated, and then the job can effectively start. So this sort of gives some flexibility into exactly how the jobs are executed and at what time based on resource availability. And ultimately, this is hugely impactful for customers who are sort of working to get those resources that are needed to do their training, because it makes the sort of essentially allows GKE and GCP all up to identify the resources that are necessary for the job to run and to pre-allocate them or to allocate them as needed for that job to be executed. Now, of course, I mentioned scale quite a bit as a critical component to any large-scale training job. And now, of course, most organizations are not going to be training at massive, massive scale. There's sort of handfuls of organizations that are training at this massive scale. But we are really proud of the work that GKE and the GCP AI infrastructure teams have done to support massive scale. Google Cloud with TPUs is actually running or has run the world's largest distributed training job as of last November for 50,000 TPU V5E chips. So this is absolutely massive when you think about just the sheer number of amount of compute that's being all orchestrated together to achieve a very specific outcome of training a model. And this was all orchestrated by Google Kubernetes Engine. So I'm really excited about sort of the work that's been done, as I mentioned before, and the continued improvements that we're going to see in more and more scale. Now, just to talk a little bit more about the scale and the value that customers are getting, we actually wanted to share an example from Grammarly. Now, in Grammarly's research on large language model alignment, Grammarly found that Google Cloud's TPUs and JAX outperformed many similar offerings that they evaluated along dimensions of performance, robustness, and reliability. So one of many examples of customers that are using Google Cloud, GKE, and TPUs together in order to do large-scale training. Now, let's move on to inference. So of course, in order to get any value out of a model, we need to start delivering that model through inference and serving. And so how do we actually do that within GKE? how do we do that in a way that we optimize our resources and leverage all of the necessary underlying accelerators like CPUs, GPUs, and TPUs for optimized inference? So first, let's break down the inference stack a little bit. Of course, we can just do inference. Inference is simply running a function against a model, right? And that's pretty straightforward to do. You put in an input and you get an output. But of course, serving is much more complicated than that. We need to actually think about surrounding that function in a way that we have the robustness that we need, that we have the observability that we need, that we can do appropriate health checking, and we can scale horizontally to meet the needs of our serving application. And this is generally where we start to talk about serving stacks within GKE. And there's a lot of different examples out there, including things like VLLM and text generation inference and TRT LLM or TensorRT LLM from NVIDIA. There's a whole bunch of examples of these implementations within GKE. But the important thing to sort of take away from this is that it's more than just inference and sort of serving is more than just taking a model and serving. And it's really about how you wrap that model with a serving stack that can fully integrate into your observability, into your scalability, and into sort of the horizontal pod auto scaling that you might have within your cluster to provide that scalable serving solution for both GPUs and for TPUs. And all of that ultimately can be orchestrated directly with GKE. Now, scaling, of course, is a huge component of any scalable inference stack. And so GKE offers 4 dimensions of auto scaling, which is, of course, going to help with meeting the demand and the needs of your AI users, so sort of the users behind the API that you might expose for your model, but also, of course, helps in optimization for cost as well as price performance. And so the horizontal pod auto scaling I mentioned just a moment ago is very critical to have within your serving stack, so you can horizontally scale to meet the needs of your users. But you, of course, need to scale the underlying nodes as well. And that's where things like the cluster autoscaler as well as node auto provisioning come in handy. So you can actually just focus on your workloads. If you were to, say, deploy this in something like Autopilot, which I mentioned earlier, you can really just focus on defining your workloads and let the underlying clusters and nodes scale as necessary. In addition to horizontal pod auto scaling, you can also do vertical pod auto scaling. So scaling up the resources that are allocated to a particular pod. And so this gives you ultimate flexibility in how you decide to scale your model and make sure you're essentially right-sizing the model for the resources that are needed. Now, GKE Autopilot is a mode of operation within GKE that provides a slightly higher level of abstraction, so users really don't have to be concerned with the underlying nodes. That essentially means that you have the full Kubernetes experience, full Kubernetes API, the same experience that we know and love within GKE. But as an operator, I just don't have to worry about the underlying nodes. This uses node auto provisioning as well as a bunch of other nice features to sort of provide that Kubernetes-based experience. And this is really important when we think about serving an inference experience. Now, as a user, I can essentially deploy my workloads to GKE and let GKE basically take care of the rest in terms of scaling the underlying infrastructure to meet the demand. And we've seen a whole lot of examples of where this has been valuable for customers. Things like 45% improvement in developer productivity. So just making it easier and more efficient for developers to go and actually deploy, not have to manage underlying resources. The pod SLA is actually a unique SLA. So instead of having sort of a node level SLA, GKE Autopilot offers a pod level SLA. So all the infrastructure is essentially managed by Google SREs. And we even saw an 85% reduction in operational costs from a number of customers in a Forrester report. So this is really important again when we're thinking about the overall reduction in operating costs and price performance that I mentioned earlier. And customers like Tabnine, they really depend, I should say, on GKE and our ability to do large scale inference using things like A3s with NVIDIA H100 GPUs to really power their business. Now, Tab 9, for those of you not familiar with Tab 9, offers an AI-powered code completion trained on permissive open source repositories. And really, to compete, Tab 9 really depends on the speed and the price performance of A3 VMs running on GKE at the kind of scale that I just mentioned before. Now, the power and scalability of the A3 VM on GKE allows Tab 9 to rapidly build, train, and serve each of their customers in the way that is personalized to their private code. So that scalability that I mentioned there is really, really critical. We're glad to see that example from Tab 9. Now, going a little bit further down the stack, let's talk about some of the foundational AI infrastructure that's really purpose-built for generative AI. Now, ultimately, in order for these applications to work either for inference or for training, we need efficient access to underlying AI infrastructure, CPUs, GPUs, and TPUs in order for them to work. So we really want to help speed up that training and inference time by offering that high performance compute as quickly as possible. And we want to do it in a way that offers the best price performance at the lowest cost. And then ultimately, we need that scale. So that infrastructure needs to be set up in a way so we can orchestrate it to scale exponentially so we can get the resources we need, all while delivering a sovereign infrastructure experience for various domestic sovereign requirements. Now, speaking of domestic sovereignty, Google provides customers customers that exist in highly regulated markets, things like public sector, education, healthcare. These customers can leverage assured workloads with sovereign controls to ensure their data, applications, and operations have that sovereignty that's needed. And GKE really is the best platform to run open source and partner models in regulated environments to provide elasticity as well as the availability for their AI models. And GKE has accreditations for both FedRAMP moderate, high, and ILv4 environments. So these are the kind of requirements that are ultimately needed for a lot of these sovereign cloud deployments, and GKE can help with that for AI models as well. Now, GKE also has the most comprehensive portfolio of purpose-built AI infrastructure. And this is really important for customers that need that level of choice. Even if they have a single model, they might need to optimize that model, move between different accelerators, ensure they're getting the optimal fit and price performance for their given workload. So everything from the C3 and H3 using Intel AMX all the way up to GPUs and TPUs, Google Cloud is going to ultimately provide the most options for your AI workloads. Everything from very large scale training, all the way down to fine tuning, all the way down to small inference. We know there's even small models that just don't need as much infrastructure. They can use the lighter weight GPUs and the CPUs. We want to be sure we're providing that level of optionality to customers. So we're really proud of that kind of choice that we can provide, and all of this ultimately can be orchestrated directly from GKE. Let's talk a little bit about cloud GPUs. Now, the A3 VM, I mentioned it a little bit earlier as well, provides 10x the networking bandwidth and 3x the training performance over the previous generation. And this is all made possible thanks to the NVIDIA H100 GPU, which is offering 26 exaflops of AI performance. It's a really powerful, best-in-class GPU offered by NVIDIA that is now available in Google Cloud. And it scales to tens of thousands of GPUs, all made possible through Google's Jupyter Data Center Fabric. And we can see lots of different examples from large-scale training to model serving, where the A3 is utilized, and lots of good examples of customers that are deploying this successfully, from Anthropic to Character, Midjourney, and Bending Spoons. Now, on the other end of the spectrum, a lot of customers don't need the large-scale H100 horsepower. They might need something that's a little bit more optimized for inference. And that's where the G2 VM comes in. That is a VM using the the L4 GPU. That's a bit of a typo there. The L4 GPU, which is really optimized for inference for workloads like generative AI workloads that we're talking about here, but also graphical gaming and other workloads as well. And so this is really going to provide that best price performance for those smaller AI workloads, the smaller models that can run on a lighter weight GPU, and ultimately it's going to deliver that that horizontal scalability and price performance that a lot of inference customer use cases demand. Now, Google Cloud TPUs, or tensor processing units, are custom designed chips from within Google Cloud that we've been building internally for our machine learning and AI use cases for many years. And we've seen rapid innovation in cloud TPUs that have been made available to our customers in Google Cloud, from the V2, the Cloud TPU V2 chip, which was first made available in 2018, all the way up to, even in the last year, the last 12 months, the V5E, as well as the V5P. E stands for efficient, and P stands for performance. So these are the sort of latest generation of TPUs that are designed specifically for large-scale inference and training workloads. Again, we can all orchestrate those directly from GKE, and customers that are deploying these can use all of their favorite frameworks, everything from PyTorch to TensorFlow to JAX. You can all leverage those directly with TPUs. Now, the V5P is a huge leap in generative AI, and we've seen this, massive performance in training, from 2.8x faster LLM training, as well as 1.9x faster embedding training versus the previous generation. So significant more power, as well as scalability. So 4x the scalability in terms of the number of TPU pods that can be deployed. And network performance obviously is critical, and the TPU V5P delivers with the highest bandwidth OCI in the market. And ultimately, we need to have some level of flexibility here as well. So we talked a little bit about the JAX and TensorFlow and some other frameworks that are available. We want to help with that level of flexibility, both in terms of the sizing, the multimodality, and the frameworks that are supported by TPUs. Now, TPU V5E is also great for inference. So we can do large-scale, powerful training with TPUs, but we can also do inference with TPUs as well. And that's where we're seeing 2.5x price performance versus the previous version, the ability to do multi-host, so we can actually distribute those workloads across multiple hosts, and significant lower latency, which is critically important for a lot of those online inference workloads. Increased 1.7x from the previous version here as well. So putting all of these things together, GKE really is the cloud native infrastructure platform for your training and your inference needs. And we know there's a lot of components that go into this. This is sort of just a high level view of some of the major parts of training and inference and some of those foundational infrastructure. But to show us how some of these things come together in a bit of a demo, I'm going to hand it over to Mofi.
All right, demo time. Hey, everyone. So we're going to take a look at how deploying this model on Kubernetes on GKE works. But before I do that, I just wanted to show you quickly the place where you can get access to these models. So there is multiple ways you can do this. Number one, obviously, we have the model in Vartex Model Garden, where you can get access to the model. But as a community, we have kind of like gathered around Hugging Face, where a lot of these models are generally stored and found. So as of this morning, Hugging Face also has Gemma, both the 7 billion and 2 billion version available in Hugging Face, as well as there is a simple interface here for you to test out some of this model that you can easily start. Like, this is running in Google Cloud using some compute GPUs, but you can test out some of the behavior of this model directly in the Hugging Face interface. The model is also available through Kaggle. If you're a user of Kaggle, you can get access to the model, the Keras, PyTorch, Transformer, C++, TensorRT, Max Text, PAX, or Flax implementation, all available through Kaggle. With that out of the way, let's take a look at just the process of deploying this model onto Kubernetes the way we would do it. So in this example, what I have here is an autopilot cluster, which is called Gemma, which is deployed on US Central 1. And for the interest of time, I deployed the model about an hour earlier than this, because, again, waiting for a cluster to get provisioned and model to deploy and download is just as fun as watching paint dry, which I don't think anybody here is more interested in. But in terms of what we need to do to get this model up and running on GKE, the tasks are as straightforward as it can be. We're defining a deployment. We are adding some labels, not that important, but the main crux here is this image that is a public image that holds a lot of the code required to serve the model using Hugging Face's text generation inference. In the upcoming release of that, probably some of those stuff would be available directly through the TGI Docker image. But at this point in time, at least, we need to go through this public image that we make available through Vertex AI Model Garden. After that, we just define how much resource we need. Again, autopilot, as Brandon mentioned, is the mode of operation where we're not really concerned with creating the node, right-sizing the node. We look at and think about how much storage, how much memory, how much GPU we would need. And autopilot will go and figure out exactly what shape of VM to provision for us. In this case, we're provisioning a 7 billion parameter model with no quantization. So it's a full-size model. So we need just about 2 NVIDIA L4 GPUs to serve this model. If you have access to a bigger model, like a GPU like A100 or H100, maybe 1 GPU would be big enough to serve this. But for L4, we would need 2 to serve this 7 billion parameter model. After that, we just set some environmental variables. In this case, we just point to the Hugging Face repository where the model is coming from, and you will need your Hugging Face hub token. Again, to get access to it, if you found yourself in this Google/Gemma-7-IT, it would ask you to just sign a consent form so that you are agreeing to the terms and condition, which mostly talks about what you can and cannot use the model for, which is mostly for safety reasons. After you have done that, you can go ahead in your settings, access tokens, find one of the access tokens. In this case, I was using this one, but all of the access tokens generally are the same. So once I have a secret created in my cluster called HF secret, I will pull that HF API token out of that and set that as an environmental variable here. So once my server starts, it will have access to this token to pull the model from the Hugging Face repository. And then we're setting some volume stuff to store the downloaded model and setting a node selector so that the right node gets targeted to deploy this application too. After that, we set up a service, and the service also is quite straightforward. It is opening up port 88,000 onto the deployment, which is the default port where TGI runs on. And as an added thing, we are also deploying Radio, which will give us an UI for us to talk to the model instead of having to deal with Carl and other funky stuff like that. All right, so let's see. I, again, ran this command just a few minutes ago to scale up my replicas to see what state we're in. kubectl get deploy. And we will see, okay, TGI Gemma deployment, and now it's 505 ready. So if I did kubectl get PO, now I have 5 replica of this running. One of them was the oldest one 2 hours ago, and the other one I just started about 10 minutes ago. So in about 10 minutes, a new node pool got provisioned by autopilot, and a container was downloaded, deployed to that node pool. And then let me see the log of one of them and see what you can see from there. kubectl logs -f. We're going to follow this log up. I had to do logs, not log. All right. So, okay, yeah, in about 10 minutes, not only we created a new node with GPU, but also started the container that had to go through and download the model state from Hugging Face itself. So I have now 5 copies of this model ready and running. What can I do with this? I have a load balancer serving this request, and Luke can go ahead and put this in the chat for folks to also go ahead and try this. If anyone wants to join me here and try out this chatbot with me, but I will be the first one to ask a question. And what can I ask? Brandon, you got a suggestion for me to ask?
Oh, that's a good question. That's a good. How about a recipe? I'm always thinking of food.
Okay.
Yeah, maybe a good recipe. I wasn't prepared with a question, Mofi, but I'm happy. I'm kind of hungry, so I always immediately go directly to food.
I'll ask about an apple pie then. How do I make an apple pie? and see what the model comes up with. Well,
And just so everyone knows too, Mofi and I did not practice what this question was. So this was completely off the cuff, completely live. And oh, look at that. Nice.
Yeah, I am not much of a cook myself, but it is talking about flour, butter, salt. It's hopefully it talks about apple at some point, because otherwise it's not an apple pie. Oh yeah, 4 pounds apples peeled and sliced, sugar, honey. That looks right to me. Again, I have to make it to test it if it actually does something, but it does look right to me. Also, Luke on the chat has dropped that link. So if anyone else wants to try, you can go ahead and ask more questions to the model to get more answers. But the thing I wanted to point out here is that not only in a matter of 10 minutes, I have a model deployed and ready for serving to the world, but also it is now horizontally scaling to 5 replica. You could also set up HPA to scale to as many replica as you have load coming in. So I could confidently say, open this link up to the world and have a bunch of people from the internet randomly try doing this thing, because I know Autopilot can keep scaling this to a maximum. I can set a limit. I don't want my cloud bill to go to infinity, but I can set a maximum and say, okay, within this limit, let this system breathe, let the system scale up to handle more load as they come in. So that was the one part of the equation. Now, the other thing I want to also show you is Kubernetes as being this heterogeneous system of where you can have multiple types of workload running at the same time. In a different cluster, I actually also have set up a single cluster that has both node pools for TPUs and GPUs. So I have a single cluster that can have your other workload as well as some large language model workload, and everything mixed in the same place so that you can use the same environment that you're used to. In the world of machine learning, we often see people using things like Jupyter notebooks as their scratch environment, but then struggle to package and make that application available to the rest of the world. In the world of Kubernetes, not only we can run the Jupyter notebook within Kubernetes, but I can have a same environment that have access to both GPU, TPU, different types of CPU across multiple zones, and all sorts of like storage options that are in the same place. So being able to create the developer experience where you are not really thinking about how do I manage 5 different environments, you are just using all your skills and all your engineering time building this one robust ecosystem, which you can take advantage of. In this example, I have, let's go find a Kubernetes cluster. Again, this is a shared project with a lot of different things, but the cluster I have is this Gemma LLM. And if I look at the nodes here, you will see that I have 4 different node pools. My default pool is generally for things that are system related. I have a GPU pool, which I decided to scale to 8. Why not? So I have this 8 G2 standard 24, each with 2 L4 GPUs. I have a TPU pool of 1 by 1 structures, TPU v5e. I have a separate TPU pool of 2 by 2, which has 4 total TPU chips in there. And all of that can exist in the same cluster, and individual node pools can breathe and scale up and down as I need it to. Now, if I were to look at my application, get pods, you'll see that I have multiple different things. This is the application that is serving the model using SaxML, using TPU. And this is the deployment and pods that are using the same TGI deployment that I showed you in the other Autopilot cluster. So this is a standard cluster, which can have like idea of node pools. You can set all this up with HPA and scale them up and down as you want to. So with SaxML, it is the API to access the model is a little bit different, but even with that, it is fairly straightforward. Again, we have, I think Luke also linked some of that in a question there, but in our documentation, we have 4 new guides for folks to try out deploying a large language model like Gemma on GKE. One with Hugging Face TGI, obviously that's the one we showed earlier. We also have VLLM, which is also very popular in the open source. We have TensorRT LLM using Triton from NVIDIA to do the same thing. If you're using those kind of setup, you could very easily use that to deploy Gemma as well. For TPU, we at this point have SaxML, but in the future, we might have even more options to do the same thing. So to talk to the model using the XML structure, this one, we don't have the integration with Gradio, but I can directly make a curl request to the model to see what data comes back. So I will copy this one, not this one, copy this request, which what it is doing is talking to the server and sending a query of the question that I want to send it to. So let me make sure that I'm still port forwarding. I am. Fantastic. And I will go ahead and change this to something else. What else can I ask? We asked about food earlier. Let's ask about something else. Other than food, I also like traveling. So what is something I must do while visiting London? Spelling London wrong. Okay. So again, that's probably a bad way to phrase that question, but let's see how Gemma responds to that. So if I were to ask, okay. So the answer is take a boat trip down the River Thames. Okay, yeah. That, another question. Someone asked, when is the best time to buy flights from NYC to Paris? I mean, if Gemma can figure that out, that would be great, because for KubeCon, I will be doing that in a few weeks. So let me try asking that question. That's a great question. I'm gonna just copy the prompt again, because I don't trust myself typing in a whole curl command. Okay, the question, I'm gonna grab it from chat here, which is, when is the best time to buy a flight from New York City to Paris? There we go. All right, the best time to buy flights from New York City to Paris is generally during the off-season months of January, February, and November. So unfortunately, KubeCon happens to be in March, so we might not get the best deal. But so the point there is that a large language model in its by itself probably is not the best place to ask questions that needs context like this, right? So we didn't talk too deep into it, but things like fine-tuning and retrieval augmented generation, or giving this model access to some of the real-time data with some flights information or things like that, that's where you can start seeing augmented superpower coming to these models, that we can make this model do more behave more like an agent than just a raw text model.
Yeah, that's a good point, Mofi. I mean, we talked about it a little bit earlier, how organizations are using open models to build new products and services. And really the way in which they're doing that is through techniques like you just described, retrieval augmented generation, essentially injecting context from something like a vector database or various internal enterprise data stores or third-party sources to provide grounding and additional context for the results. So yeah, it's a good question, a good comment to make there on how you can actually make that use case real.
Yeah, for sure. So also with the VLLM or TJ implementation, the model will work out of the box with things like LangChain. So if you want to build those connections yourself, I have tested some of the RAG capability last week. And again, if you're doing the TJ implementation, a lot of the things, just if you're using those LangChain libraries to talk to anything served by TGI, you can just do that, right? You don't have to really do anything special to talk to Gemma, which kind of also is really great, because if you're used to building an application with LangChain in a certain way, and you want to try out the Gemma model, you just almost in place swap the existing. If you're using something like Mistral or Llama 2, swap it out with Gemma and see if that does anything better for you. We also have documentation, if or not already out, will be out in the next couple of days, on how to fine-tune this model using your own data set. And then you can start thinking about some of the ways you can make this model really work for you or for the use case you're thinking about.
Mofi, I wanted to come back to something you mentioned earlier. In your cluster, you have both TPUs and GPUs deployed sort of alongside each other. And you talked about the flexibility that delivers for customers. I kind of want to make that a little bit more real for the audience as well, to sort of think through different scenarios in which having a TPU alongside a GPU, maybe in the same cluster, makes sense. Can you sort of think of a scenario, especially maybe even related to retrieval augmented generation or something like that, where that ability to switch between a TPU and a GPU, or maybe have part of your workload deployed in a TPU and part of your workload deployed in a GPU, sort of makes a whole lot of sense.
Yeah, I mean, one of the thing I can just think at the top of the head is TPUs are really good at efficiently training your data. So if you have like some data set that is constantly evolving and you have some sort of like a weekly schedule to train or fine tune this data to keep it up to date, you could have that done on TPU, but the output of that model can then be served using some GPU. Because at the end of the day, all TPU and GPUs are writing to some sort of file format, which if they're using PyTorch, which both TPU and GPU can do, you can train your model using TPU and then write those output as checkpoints as something that your GPU can then serve. And you can really start seeing the cost benefit of using a really fast, efficient chip like TPU, but also get commodity hardware like GPU to serve those into your system as well. I mean, again, TPU can do inferencing as well, but if you already have investment in the GPU world and you want to continue using that, you can get kind of the best of both worlds.
Yeah, it's a good call out. I mean, we've seen other examples where customers are deploying a specific model, say that's compatible with JAX, as an example, like a stable diffusion model that's compatible with JAX. But there might be other parts of the sort of pipeline that are generating the image in that particular use case that maybe aren't yet compatible with TPUs, and they want to run those on GPUs. So it sort of allows, I think, and maybe as another example, even just on the inference side, it allows flexibility. So you can have maybe one service that's just doing the inference of a model be running on a TPU, but if there are other things, embeddings or other aspects of your application that say require GPUs, you can actually have them working together in the same cluster.
Yeah, and more what we're seeing is you have your access to things like Gemini via API. Your applications are talking, but for something very specific, you have fine-tuned one of the models, one of the smaller models. Again, calling a 2 billion or 7 billion parameter model so small sounds pretty absurd coming from like the concept of 2022, 2021. But again, with existence of model that touches almost the trillion parameter mark, billion probably sounds pretty small comparatively. So you could have I think in the next few months, we're going to start seeing examples of in the same place running multiple of these small large language models, and that are like fine-tuned to do specific tasks. And then in the same application, you can start like hooking them all up together using something like LangChain to do various specific things and getting like agents like behavior. That is going to be pretty exciting once people start doing things like that.
Awesome. Couldn't agree more. Very exciting time. So with the last 7 minutes we have, Mofi, unless there was anything else you wanted to share on the demo front, we'll go to questions. Well, it's up to you, Mofi. Anything else on the demo before we?
No, I think again, like the best part of all of this is how quickly and easily you could do things. And again, I think Luke also shared some of the links in the chat on how to do that all in GKE. We have some other links to do that in Colab. So if you want to just try out, like just testing on a Colab has like a free tier that you can try it out without having to do anything in terms of like billing. Also, there is a chat interface directly embedded into Hugging Face if you want to talk to the model a little bit to see how the model behaves. I know people have like a list of questions they usually like to ask these chatbots to see how they behave. So we could try them out with Gemma. And again, it was a very cross-functional effort from all across Google to make this model as widely applicable to as many different folks. Like we have the C++ implementation already out. We have the PyTorch, Keras with Hugging Face. So it was basically coming out at the same time on like 10 different output version, which is pretty daunting. And again, this happened as of this morning. So it is very opportune time for us to be able to come and share all of this today. Any other day would probably not be able to share this much at the same time. So yeah, we could not have planned this any better if we planned. So this was amazing that we could share this.
Awesome. So with that, we will open it up for any additional questions. If you have questions, feel free to drop them in the chat. We'll do our best to answer them live here in the session. And while we're waiting for some additional questions to come in, just wanted to reiterate maybe for the audience, like what's the easiest way to get started? So if I'm looking to say deploy an open model like Gemma, or maybe a different open model, like what's just the fastest path to get started?
The fastest path would be probably with text generation inference with TGI on GKE. VLLM and TGI share very similar architecture, so they probably are fairly equal. And the reason I say that's the easiest and fastest is because of the popularity of TGI. A lot of folks are already probably familiar with that kind of way of deploying LLM to Kubernetes. So that would probably be the most easiest way to wrap your head around what you're doing. And then again, after that, we have documentation on how to do that on Triton or SaxML. So if you want to check out that kind of architecture, how you can do that way, we have that as well.
Awesome. Yeah, that's great guidance. Super easy, well-established inference stack. It has all the things you need to get started, logging and observability and health checks and things like I mentioned before, and all supported in the open community. So great place to get started, absolutely. Other question I had for you, Mofi, there's been sort of a lot of discussion, especially over the last week or so, about Gemini and API-based models and Gemma and sort of these sort of smaller models, lightweight models. Kind of be curious to get your perspective on some kind of use cases folks, listeners should be thinking about for the smaller models versus sort of the larger API-driven use cases, I should say, for like something like a Gemini.
Yeah, so I mean, we were talking a little bit about this earlier, but generally is that if you think about that you have some sort of like data set that that exist, and you can think of fine tuning is going to get you a better result in general. Like for models like Gemini Pro and Ultra, you can do some augmented generation with RAG, but you can't necessarily fine tune the model itself, right? Like you wouldn't be able to change how the model behaves on a day to day. So with things like Gemini 1.5 with like a 1 million token of context, you can achieve a lot. But again, at the same time, unless you really need that 1 million token context, you're actually probably spending more than you need to with sending all 1 million token. With something like RAG, you can actually, there was a paper earlier this week that I read, is that even with like sending less token, by doing some pre-work of sanitizing some of the data, you can get similar, but not, if not as good as data, but you can get very close. So there is going to be, over the next years, I feel like it's going to be a lot of optimization in that front where, okay, I could send 10 million token, but do I need to send 10 million token? So we're going to see probably other like more specialized use cases. Okay, I'm going to fine tune this model to be really good at doing car fixing advice. And then I'm gonna have Gemini, like Gemini Ultra or Pro underneath to have fallback or like some out of the box questions. But if any question comes that are regarding fixing cars, I have this one model that I fine tune, and that is really good at doing that one thing, right? So I think we're gonna start seeing more mixed use cases where folks are like creating these fine tunings on specific use cases, but also have this underlying like fallback option that are generally good at most things, right? So that's going to be like a interesting way how people are thinking about like composing their application, almost like building blocks.
Yeah, I couldn't agree more. And we're excited to see what the community is going to do. I mean, today is day one. Excited to see how Gemma evolves and all the great things that you developers do with Gemma and all the different use cases you can find. So I'm really excited for that. So we are almost out of time. Maybe we'll just flip back to the slides here for just a brief second and just share with you some of the resources that are available for you to get started. So here is the docs link. So this is the most up-to-date documentation on all things AI on GKE. So if you want to deploy the Gemma model, just like Mofi showed, you want to deploy it on TPUs, on GPUs, you want to do fine tuning, you want to do all sorts of things. Those are all on our docs. So I encourage you to go and check those out. We also have a bunch of tutorials for some more advanced use cases that are available, and you can see that link on the bottom right. As always, feel free to reach out to us. Talk to a Google Cloud specialist. Reach out to us directly. We're always very happy to have a conversation and dive deep on this stuff. And then lean on our ecosystem. We've got great partners out there who are building amazing applications with AI on GCP, and so don't hesitate to reach out to those experts as well. So with that, thank you all so much for your time and attention today. It's been a great session. Looking forward to future updates, and thank you all for the time.
At Google Cloud Next, we're announcing an amazing show.
All right, cue the music.
We're building the new way to cloud.
So that just means we get to think even bigger.
And now, helping you connect like never before.
Let's start with development.
I'm loving this. Super cool.
AI is going to change the game for all of us.
Live on the demo stage.
I can't tell you how excited I am to continue blowing people's minds.
We're now in the midst of one of the most profound technology shifts in history. There's so much more for all of us to explore together that'll power this next chapter of digital transformation.